Now we will start the chapter Kinematics of Circular Motion. So first see what is a circular motion. Circular motion is rotation along a circle, that is a circular path or a circular orbit. Circular motion can be either uniform or non-uniform. With uniform circular motion we mean that the angular rate of rotation is constant, and in the non-uniform circular motion the angular rate of rotation is not constant and it is varying with time. Now let's see some definition. First we'll define angular displacement. Angular displacement is the angle subtended by the arc traveled by the object at the center. So let's see this with the help of an animation. So here we can see that this delta S is the arc of a circle, and this is the center of the circle. Let's say this O. So an object travels from point A to point B, making an arc, the length of which is delta S. R is the radius of circle. So as we can see here, this arc makes an angle delta theta at the center. So we can say that the angular displacement of the object when it moves from point A to point B is delta theta. Now let's see what is the direction of angular displacement. The direction of angular displacement is going into the plane for clockwise rotation, and for anti-clockwise rotation it is coming out of the plane. The magnitude of angular displacement is given as delta S by R, where delta is the length of the arc and R is the radius of the circle. And in vector representation we can write delta theta, which is our angular displacement, as R cross delta S by R square. So let's explain this. So here we can see that we can write delta theta as delta S by R, where delta S is length of this arc and R is the radius. Also in vector representation we can write delta theta as R cross delta S by R square. Here the direction of radius vector is radially outwards, so this is our R vector, and direction of delta S is tangential to the arc. So if this is the arc, then the direction of delta S would be tangent to it, so it would be perpendicular to the radius vector. This is our delta S. And this angle is 90 degree. So we can see from here the direction of R cross delta S would be going into the plane for clockwise rotation, and for anti-clockwise rotation the direction of delta S will change. It will be here, and so the direction of delta theta would be coming out of the plane. Now we will define angular velocity. First we will define average angular velocity. Average angular velocity is denoted by omega, and it is defined as delta theta by delta t, where delta theta is the total angular displacement and delta t is the total time of journey. Similarly we can define instantaneous angular velocity, which is rate of change of angular displacement of an object. So omega will be limit of delta theta by delta t, where delta t tends to 0, or it is d theta by dt. Similarly we can define angular acceleration. Angular acceleration is denoted by alpha, and average angular acceleration is defined as the change in angular velocity divided by the time interval during which the change has occurred. So alpha will be equal to delta omega by delta t, or it will be equal to omega 2 minus omega 1 by delta t, where omega 2 is the angular velocity at the end of time interval delta t. At the end of and omega 1 is the angular velocity at the beginning of time interval delta t. Now instantaneous angular acceleration will be rate of change of angular velocity with the time. So instantaneous angular acceleration alpha can be written as d omega by dt.